Okay, hello everybody in, I think it's group 4. Again, profuse apologies for having missed the class on Tuesday last week. I'm going to go through the solutions for you by way of recompense. So we were looking at question 17 to start with, and these questions are about the speed at which certain functions grow. So we say f of x grows faster than g of x if f of x over g of x goes to infinity as x goes to infinity. And if you kind of put 1 over these on the other upside down fraction, you can see that it's the same thing as saying that if you have g of x over f of x, then the limit of that goes to 0. Okay, right. So the warm-up question is to show that for every m in n, no matter how large, e to the x grows faster than x to the m. Okay, so we want to calculate, so solution, let's recall that e to the x is equal to 1 plus x squared over 2 plus plus, I'll just give a couple more terms, x to the m over m factorial plus x to the m plus 1 over m plus 1 factorial, and then I'll leave the rest out. Now if we're looking at what happens when x goes to infinity, the limit of that as x goes to infinity is certainly going to be, we don't have to look at negative numbers. We can look at just the positive numbers. And in that case, that's going to mean that everything in here, every single term, is itself positive. Now, often when you have a big thing like this, if you're trying to work out what the limit of this function is over this function, it's easier to just pick out one of these terms, and in this case we're going to just pick out this one. So we have e to the x is going to be bigger than or equal to this term, because we've got lots of other ones as well. So x to the m over m plus 1 factorial. And so e to the x over x to the m is going to be bigger than or equal to x over m plus 1 factorial. So that's just dividing both sides by the positive number, which is x to the m. Okay, so now let's just take the limits. So as x goes to infinity, x over m plus 1 factorial, so this is just a constant, this is going to infinity. But this is always bigger than this. This is always bigger than this. So if this goes to infinity, this one must do too. So this implies e to the x over x to the m goes to infinity. Right, so that's question A. For question B, there are some nice substitutions here. So if we can do e to the x over x to the m, and we're looking at doing log of x and x to the beta for some beta, then we must be looking at something similar to this. So if we can, because we'd just be looking at kind of inverse functions. So if we can kind of try to convert this into this format, then we should be okay. So that's the idea, and the two substitutions that are going to be useful here. So first of all, to say that y is x to the beta, and then after that we're also going to want y is e to the z. But we want to calculate the limit as x goes to infinity of, let's do it this way, log x over x to the beta. I want to see whether that is going to be 0 or something else. Okay, so let's try the substitutions. So if I put in y is x to the beta, that's going to be, since beta is positive, that's if and only if you take the bth root of both sides, you get y to the 1 over beta is x, and we may as well do this one as well. If y is e to the z, then the inverse function in this case tells us that z is log of y. So now, just plugging those in here, I get that the limit of this is equal to the limit of, so putting y in there and putting x in there, I get log of y to the 1 over beta. But we've now, you can use laws of logs and pull 1 over beta outside of this. If you've got log a to the b, then that's the same as b log a. So you can pull that out and you get 1 over beta times the limit as x goes to infinity of log y over y. And then we use the substitution, so if I put in z there and e to the z there, then I get 1 over beta times the limit as x goes to infinity of z over e to the z. Well, that's just the case where m is 1. Since we've shown earlier that e to the z over z goes to infinity, that's going to say that z over e to the z goes to 0. So this is equal to 0, and that shows us that x to the beta grows faster than log of x. So x to the beta grows faster than log of x. The rest of these, that is all that we need to do for that question. For question 18, this is about just looking at a little bit of the power series of e to the x and trying to say something about that relative to log. So let's try and do it in the order that we're being asked to. We want to consider e to the x and show e to the x is bigger than or equal to 1 plus x all the time. Okay, so we're given some hints first of all to see that it should be easy if x is less than or equal to -1 or if it's bigger than or equal to 0. So this is true if x is less than or equal to -1. What happens? Well, this number on the right here, 1 plus x, is then less than or equal to 0, but e to the x is always positive. Now, if you think about the graph of e to the x, it's never negative. So it is clear that this is going to be true when x is less than or equal to -1. But it's also going to be true if x is bigger than or equal to 0, because we have e to the x is equal to 1 plus x squared over 2 factorial plus whatever. If x is bigger than or equal to 0, all of these terms are, and so this is bigger than or equal to 1 plus x, just to get rid of those positive terms. Where it is a little bit more difficult is in the middle. So if x now, we can assume that it is between -1 and 0, then we want to see why this is still true. So let's still stick with the power series here and see if we can show why some of these terms can be taken to be bigger than 0. So I'm just going to write a couple more of them out. And use the technique that we use many times in this course, which is just to pair up terms. Sometimes you pair them, sometimes you stick them in more than pairs, but in this case that will do. And then the idea is to put them all over a common fraction and factorize. So I'm going to get x squared into, so this is 3 times 2 times 1, and this is 2 times 1. So if I put them over the common denominator of 3 times 2 times 1, I just have to do 3 of these, and then I can add this one in. So this is just 3x plus 1 over 3 factorial. And this is x to the 4 into, again, I'm going to get a 5 if I put a 5 on the top and the bottom. That's going to give me 5 plus x over 5 factorial plus dots. So because this is an x squared. This is always bigger than or equal to 0. In fact, it's going to be bigger than 0. And if you look at this, the numerator in this fraction, well, sorry, got this wrong. Should be 3 plus x, and that's 5 plus x. If you look at the numerator in this fraction, because x is always always bigger than -1, the 3 is always going to be bigger than the magnitude of x, and so this is also going to be bigger than or equal to 0. Similarly, if x is bigger than or equal to -1, then this is always going to be positive, and so is this. So that tells you that e to the x in this region as well is bigger than or equal to this. So e to the x is bigger than or equal to 1 plus x here as well. Okay, and then we go for a few substitutions similar to what we did before to see that we can get some interesting information about log. So the log of y is, or let's say log of 1 plus y is defined for y bigger than -1. And it's an increasing function. So if I apply log to both sides of this expression here, then it's going to keep the direction of the arrows. So log is an increasing function. So log of 1 plus x, just taking the log of that, is going to be less than or equal to x. And we've just written the same thing but with x instead of y. So I won't just write that with y in it. Okay, and then we do a couple of other interesting little substitutions. We want to show that the log of n plus 1 over n is less than or equal to 1 over n. So just putting, put y equals 1 over n, and then we get log 1 plus 1 over n is less than or equal to 1 over n. So that's fine, just a substitution. And D, similarly, we're going to put in y is -1 over n plus 1 to get log of 1 minus 1 over n plus 1 is less than or equal to -1 over 1 over n plus 1, and let's see what we get. We get log of, putting this over the common denominator of n plus 1, we get n over n plus 1, and that's less than or equal to -1 over n plus 1. So if I times both sides by -1, I get this. Right? Because if you times by a negative number, then it is, you have to swap the sign around. But now we can use laws of logs here. So if you've got minus log of something, then that's the same as log of that thing to the -1. And if you've got a fraction to the minus 1, you just swap it over. So that's the same as log of n plus 1 over n is bigger than or equal to 1 over n plus 1. So part E is where all the fun happens. We want to have a look at the harmonic sequence, which is 1 plus a half plus a third plus 1 over n, and see what we can do with this. Well, C tells us that each one of these terms is bigger than or equal to log of n plus 1 over n for each one. So let's say, so we can put that this is bigger than or equal to, so if n were 1, we would get log of 2. If n were 2, we would get log 3 over 2, and you just keep going, 4 over 3 all up to log of, so 1 over n is bigger than or equal to log of n plus 1 over n. And miraculously this simplifies, because you can use the laws of logs to write log a plus log b is log ab. So you just multiply all these things together and you end up getting that this is equal to log of, well, we can pretend there's a 1 there. We're just going to get log of n plus 1. Right. Which is certainly bigger than or equal to log of n. And so if I now take that over to the other side, I'm going to get that 1 plus a half plus a third plus 1 over n minus log of n is bigger than or equal to 0, which was one of the things that we were supposed to get. And now we've also got to get that that this is less than or equal to 1. So we'll do that the other way. If I've got 1 plus a half plus a third plus 1 over n, I know that that is going to be, using part D in this case, it's going to be less than or equal to what happens when I replace each one by log of, so like log of 3 over 2 and log of 2 over 1 and so on. So I'm going to leave the 1 alone. So this is bigger than or equal to 1 plus log of 3 over 2 log of 2 over 1 plus log of 3 over 2 plus all up to log of n plus 1 over, also that should just be log of n over n minus 1. Because this last thing, if I want to use d on it, I've got 1 over n, and I want to replace it with something bigger, I've got to put the n on the top and then put 1 less than it there. Okay. So again, all this stuff is going to end up cancelling, with the exception of the top and the bottom terms here. So we'll just get 1 plus log n. So you get log of a times log of b. Log of a plus log of b is log of ab. So the 2's cancel and you get the 3's. Similarly, they all cancel all the way down. So this tells you that 1 plus a half plus a third plus 1 over n minus log n is less than or equal to 1, which is what we were supposed to show. Right. And there's some other comments about that just there. We'll just do the last one here, question 19. So this is to just differentiate x to the 5 by definition, and you are not supposed to use the fact that you know how to differentiate x or any products or anything, or even the fact that it's linear, and so you can differentiate different terms and add them together. We're not using any of that. We know that differentiation by definition is a limit. So the definition of the derivative of a function f at a point A is just going to be the limit as x tends to A of f of x minus f of A over x minus A, if it exists. Of course, there are examples of functions that are not differentiable, and so you can't find this necessarily. Okay, well, it's just a case of plugging in the what f is, and it's just x to the 5. So this is equal to the limit as x tends to a of x to the 5 minus a to the 5 over x minus a. But I can factorise the top here. So this is basically the factor rule. If you plug in x is a, the top vanishes, and so that tells you that x minus a is a factor. And then I can work out how to factorise this by just going down it bit by bit. X to the 5 I get from those two terms. That gives me a minus a to the ax to the 4, which I then need to add back in again, which I can do if I put in that term, ax cubed, and that gives me minus a squared x cubed, which I can get if I add back in a squared x squared, and you can see by now what's happening. The a's are going up and the b's, and the x's are coming down, and we finally end up with that value. And we're still taking the limits. Right, well, this function has an x minus a and x minus a here. As long as x isn't equal to a, I will always be able to cancel the top and bottom of these. So I end up with just a normal thing to do, to just work out what the limit of x is, of x tending to a of the following thing is. and you plug in a into this, and what do you get? You get a to the 4 plus 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 a to the 4. So that's 1, 2, 3, 4, 5 of them, which is equal to 5a to the 4, which is exactly what we are expecting to find when we differentiate x to the 5 and then plug in a. So, hope to see you on Tuesday.